The more unknown sources are false paths. So, false paths, they cannot be excited because of the logic of the circuit is such that, so they cannot be excited. So, what we can do, if there is a false path, then we can put a 0 control point, so that this path is forced to 0, or we can have one control point. So, whatever we do, whatever is the requirement based on our analysis. So, we will be putting it to one of those control points, so that the false path gets excited. So, it gets a value of 1 or 0 as desired. Then there are critical paths. So, critical path, the problem is that adding an extra input pin to a selected combinational gate on the critical path. So, this is one inverter. So, this inverter gets input from X, this is on a critical path. So, this is in this case. So, this is the inverter is there. Now, if this inverter is there, then one possibility is that we do not want to increase the delay that occurs in the operation of the circuit. So, what we do, we put a NOR gate and the BIST mode control comes here. So, this way we can introduce an embedded 0 control point. So, if we want to make this X as 0 at this point always, due to the creation or due to the removal of unknown, then we have to do it like this. So, we have to embed a 0 control point in this fashion. On the other hand, if we require that this point should be 1 after this in the BIST session, this point should be 1. So, for that purpose we have to embed one control point. So, in that case, in the BIST mode, so it has to be inverted and then it goes through a NAND gate. So, you may notice that we are not increasing the delay, like delay of this path was 1 gate. So, here also it is 1 gate, here also it is 1 gate. So, for critical paths, so we add one extra input pin to a selected combinational logic on the critical path. Now, there may be multiple cycle paths. So, that is the data is available after multiple cycles. So, maybe the delay of the system is such that the combinational logic does not evaluate in one shot. So, that way, if we have got multiple cycle paths, so for the circuit requires multiple cycles to get stabilized. So, we have got we can introduce one 0 control point, 1 control point, or we can hold certain scan cell output states. So, we can hold the scan cell output, so that they do not change their values during this multi cycle operation. So, that is another way of stopping this unknown sources. Then floating ports. So, primary input and primary output may have a proper connection to power VCC or the ground. This primary input, so floating port, some port which is floating. So, we can put this input, primary input or primary output to some proper values. Floating inputs to any internal modules must be avoided. So, we should not have any floating input for internal gate, internal portion, but for the primary input and primary output, so we can connect we can connect them either to power supply or VCC or the ground in the BIST mode. Bidirectional IO ports. So, this is another problem. So, because in this is the normal operation in the when the scan enable is 0, then and in the BIST mode is also 0, then this one comes as a 0. Now, if the enable line is enabling this this buffer, then this D value is available at the output pin. Otherwise, this pin is acting as input pin. So, value comes through this. Now, if we do not want that, if we want that this bidirectional pin, so what we may want is that we want to configure it as output mode in the during BIST operation. So, during BIST operation, this BIST mode signal is 1. As a result, this is 1, this is 1, and this one, whatever be the value of this enable line, whatever be the value of this scan enable line. So, this line will get a 1. As a result, this port will be configured as an output port. So, we can fix so in this case we have fixed the direction of this IO port to output mode. Similarly, you can have some circuitry on the lower side for this Z. So, we can control this line to be always input in the BIST mode. So, whatever is required, whether we want to sense a line as input or output. So, we can put a control over that. Sometimes we need to do a retiming. So, retiming are basically needed when there are races or hazards caused by clock skews, because the test pattern generator. So, our basic module is like this: there is a test pattern generator, there is a circuit under test, and there is a response analyzer. Now, each of them may operate on a different clock. So, this test pattern generator may work on clock 1, test circuit may be operating on some clock 2, and this ORA may act as a clock in a separate clock CK3. Now, there may be problem with this clocks, because in when you are, if they are the same clock, then distribution of the clock into all these modules. So, that will create that may create some clock skew. Okay. So, what is done is that the retiming logic is added between this test pattern generator and the circuit under test, and between the circuit under test and the output response analyzer. So, even if these clocks are different, so they are out of phase, there is a clock skew, means we can think that as if they are 3 independent clocks, clock 1, clock 2 and clock 3. So, these 2 D flip flops are added to operate on the clock 2, and 2 D flip flops are added to operate on clock 3, so that the problem of skew will not occur. So, this is the retiming logic that is added, which will avoid the clock skew. So, this is required to be done, this modification has to be done to the circuit. Now, how do we generate the test pattern? So, these are the rules that we have seen while modifying a circuit or making a circuit BIST ready. Some modifications are to be done, so that these unknowns do not come into the BIST operation, and this clock skew problem do not occur in the BIST operation. Similarly, this tri-state buffers, so they are also taken care of, bidirectional IO they are taken care of. So, all to ensure that these unknowns do not come into the operation of the system, because then this response analysis will become wrong. So, while doing the test planning part, so we had assumed some values for those points, but in reality when it operates, it comes up with some other values. So, if the values are unknown, so then the values may be different. So, as a result, the final response or the golden signature may not match with the response that we get from the circuit under operation, and even if the circuit is correct, so it will be identified as a faulty circuit. So, that is why all these X's need to be blocked, okay, and this clock skew problem has to be solved. Next, we look into the test pattern generation process. Now, how this test pattern can be generated? Now, you see that typically this deterministic test pattern generator, so it has given us a set of test patterns. So, as a test pattern generator, what we can say is that we can have a memory where all these test patterns are stored, and we can have a counter sort of thing that can produce addresses for the memory, and each at each count value it outputs one particular pattern, and that is going to be applied to the circuit. So, that is the standard AT type of operation, but when we are talking about this BIST operation, we do not have such a sophisticated mechanism. Okay. So, we need to make this test pattern generator very simple, and also this response analyzer also have to be very simple. So, there are many such configurations, many such circuits that can act as test pattern generators. So, in most of the cases they are constructed from linear feedback shift registers or called LFSRs. So, apart from these linear feedback shift registers, so you can use some counters as test pattern generator, you can use cellular automata based structures for this test pattern generation. So, they are also there in the literature, but for our course, so we will be restricting ourselves to LFSRs. Now, this test pattern generation philosophy, so it can be for different types of situation, like we can try for exhaustive testing. So, exhaustive testing requires that all patterns are to be applied to the circuit for testing. Then pseudo random testing. So, this is basically a random testing, but it is pseudo, that means after some after generating some pattern, so it will repeat itself, that is a pseudo random testing. And pseudo exhaustive testing. So, it is not exhaustive at all the points, like if it is an n input circuit, maybe it is for k inputs it is exhaustive. So, other places it is not exhaustive. So, there are a subset of outputs for the test pattern generator, where the generated pattern is exhaustive in nature. So, that can be there. So, one standard LFSR, it was proposed by Golomb in 1982. So, it consists of n number of D flip flops and a selected number of exclusive OR gates. So, we have got this thing. So, this is an n stage, this is called external XOR LFSR, because the XOR gates are at the they are external to the cell. So, these are I0, I1 and these are the flip flops that we have, and then depending. So, this H value, so H they are actually switch, whether this output goes to this XOR gate or not. So, that is controlled by this H. So, if H n minus 1 is 1, that then this output will be XORed, then this n minus 2 is 1, then this will be XORed. So, you see that the value that is coming back to S I 0 is nothing but a weighted sum of all these previous values H 1, H 2. So, this is the current this is the output of S I n minus 1, and then it is H 1 times this one, H 2 times this. So, that way it is a weighted sum of the previous stages. Another one is known as modular LFSR. So, in modular LFSR, this XOR gate is placed between two adjacent D flip flops. So, the structure is slightly different. So, between two adjacent flip flops, so we have got this XOR gate put, and this whether this value will be XORed here or not. So, that is controlled by this switch H 1. Okay. This H 1 will be controlling that. So, the advantage of modular LFSR is that you can very easily add further modules, further more flip flops to this chain. So, extending this thing becomes easy. Though functionally this modular LFSR and this one, this external LFSR, external XOR LFSR. So, they are going to be same, standard LFSR and this modular LFSR. So, both of them can realize similar set of functionalities, but both the structures are there. So, there is a very strong theory based on polynomials that can describe the properties of these LFSRs. First of all, this internal structure of n stage LFSR, it can be described by a characteristic polynomial of degree n f x. Okay. So, f x is 1 plus h 1 x plus h 2 x square plus h n minus 1 x power n minus 1 plus x to the power n, where h I is either 1 or 0 depending upon the feedback path. So, you see, so 1 plus h 1 x. So, this is actually if we say this as 1. So, this is one step before that. So, this is h 1. So, h 1 x, one step back before that h 2 x square, that way it is coming. So, h n minus 1 x n minus 1 x power n minus 1. So, that is, and x to the power n is the value that we are computing. So, that way this polynomial is representing the connection pattern. So, wherever these h i's are 0 or 1. So, if it is 1, that means on the feedback path this particular term will be there. So, that XOR gate will be there in the circuit, and if it is not there, that means the XOR gate is not there. So, content of the LFSR at any point of time can be represented by SI. So, SI x is the polynomial representation of SI. So, this is again given by SI 0 plus SI 1 x, SI 2 x square. So, these are basically the contents of the values at various points, and if the value has to be considered, then it is this term will be 1. If this is 0, naturally this is, so the SI 0, SI 1, SI 2. So, these are the values of different flip flops, and if it is 1, that term x power of x is coming into picture. If that term is 0, then it is not coming. So, content of the LFSR is represented again by a polynomial. So, there is there is these LFSRs, they show some periodic properties. So, if t is the smallest positive integer such that f x divides 1 plus x to the power 10 x to the power t, then the integer t is called the period of the LFSR. So, the thing is that if you have this LFSR, then after time period, after t such shifts, like if you initialize the LFSR with some pattern and then just go on giving clocks to the LFSR, then it will go on evolving itself, and in the evolution process, after t clock cycles, it is going to repeat the sequence that it is generating. Okay, sequence in the sense the sequence of the content of different cells that are there. So, that is going to be repeated. So, this T is called the period of the LFSR. So, it gives rise to many interesting properties, like see say this one. So, here we have got, so if we count it as say this standard LFSR. So, if we count it as 1 x square x cube x to the power 4, then you see that while doing this addition, so we are taking the terms like say this 1 is definitely there, plus this x square term is coming and x to the power 4 term is coming. So, they are summed up and it is fed to the first flip flop. And in case of modular LFSR also, it is 1 x square x cube x to the power 4. So, x to the power 4 is definitely coming. So, in all the cases you see that from the last cell we are always taking the feedback. Okay. So, this x to the power n term is always present. So, there is no switch to control it. Okay. So, this x to the power n term is always there, but otherwise it is coming from this other delayed terms. Okay. So, here it is 1 x square 1 x square x cube x to the power 4, here it is 1 x square x cube x to the power 4. So, these appropriate terms are getting added. Now, you see that this is a 4 stage standard LFSR. So, if you start with the pattern 0001, if you feed it the pattern 0001, then after after one cycle what will happen? So, this is basically the sum of the second cell and the last cell. So, 0 and so this 0 and this 1. So, 0 and 1 they are summed up. So, value is 1. So, you see that value is shifted onto this flip flop. So, this value becomes 1 and rest of the bits, so they are just shifted. So, this these 3 bits, so they are getting shifted through this shift register, they are becoming 0 0 0. In the next, this this second cell and again the second cell and fourth cell they are XORed. So, second cell fourth cell XORed, the content is 0. So, that is coming back to the first cell. So, this is becoming 0, but this 1 shifts to the next cell, this 0 shifts to the next cell, this 0 shifts to the next cell. So, we get 0 1 0 0. So, in this way you see that after this many patterns like 1 2 3 4 5 6, after generating 6 patterns, so it is repeating itself. So, this has got a period of 6. So, on the other hand, if you look into say this particular pattern, so this particular LFSR, so it start with 0001, and if you just follow the logic that is captured by this, so if we are going to, if we are giving clock signal clocks to this flip flops continually, so after initializing with 0001, so the value that will be computed at the first cell, so this 1 is coming back to the first cell. So, 1 comes here, the second cell gets the sum of the last cell and the first cell. So, so the 0 and 1, so they are actually XORed. So, you get a 1 at this point. So, this way this shifting is going on, and interestingly, so this gives a much longer sequence, you see, and it has repeat itself, like after generating 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15. 16th pattern is repeated. So, it has got a periodicity of 16. So, 16th pattern is going to be repeated, and content of any at any point of time, if you see the configuration. So, this S0, the initial configuration is x cube, because this bit is set to 1. So, this bit, the initial configuration S0 is x cube. So, okay. So, this is 1 x squared x cube. So, that way this content is x cube, this cell is x cube. So, that way the initial value is can also be represented by a polynomial. Now, there is a concept of primitive polynomial. So, primitive polynomial says that the polynomial, the characteristic polynomial, if it is if I have got some characteristic polynomial f x, and if we are trying to figure out this type of polynomial 1 plus x power m, such that f x divides 1 plus x to the power m. Okay. So, we are looking for the value of m, so that this is this f x will divide x to the power m. Now, if this f x to the power m, this m happens to be 2 to the power n, okay, where this f x is an n degree polynomial, this happens to be 2 to the power n, then we say that this f x is a primitive polynomial. So, this is that. So, primitive polynomial, if it is there, so it has got the property that it will be repeating the patterns generated after generating all 2 to the power n patterns, or basically not all 2 to the power n, 2 to the power n minus 1 pattern. So, all 0 it will not generate, but accepting all 0 it will generate all the patterns. So, you start that LFSR with any pattern, any non-zero pattern. So, it will generate all the 2 to the power n minus 1 pattern, then only it is going to repeat itself. So, that way this type of polynomials are known as primitive polynomials. So, if an LFSR has got this property, that means we can use it for test pattern generation, because it will generate a large variety of patterns. So, it is not going to repeat in a shorter cycle. Okay. So, there is the many experimentation has been done to find the exponents, the polynomials, this type of primitive polynomials. These lists are available. Like if you are trying to formulate a polynomial of say degree 24. So, in this 24 we see that it is written 4, 3, 1 and 0. So, x to the power 24 term will always be present, because that is x to the power n term, but the remaining tapping points will be at 4, 3, 1 and 0. So, this becomes the primitive polynomial for 24 for n equal to 24. So, this list is available, and in fact, this list is available up to I think up to 512 number of 512 n equal to 512. So, this list is very big, that is available. So, for our purpose, whatever polynomial we need, whatever if I have got say if I have got this LFSR to act as the test pattern generator, and we see this, that we have to feed to some circuit, and this circuit has got say 100 inputs. So, one straightforward way may be that we use an LFSR of length 100, it has got 100 bit LFSR, and feed this directly to this. So, these patterns that are generated by the LFSR will be fed to the circuit as test pattern. Okay. So, if it is a primitive polynomial, it will ensure that it will not repeat its sequence before generating 2 power n minus 1 new patterns. So, we will look into many testing techniques for this BIST environment. The first one is known as exhaustive testing. So, exhaustive testing means we apply 2 power n exhaustive patterns to an n input combinational circuit under test. So, and exhaustive pattern generation. So, there can be a binary counter. So, binary counter, since we want to generate, we want to apply all 2 power n patterns. So, if I have a binary counter that goes from 0 to 2 to the power n minus 1. Okay. So, it generates all those patterns, then of course, we can use it as a exhaustive pattern generator. Other possibility is that we can also use LFSR, but LFSR, the problem is it does not generate all 0 pattern. At any point of time, if the LFSR has become, its content has become all 0, then it is just going to remain at that state, it is not going to be updated. Okay. So, that LFSR has to be the LFSR has to be modified, so that it generates all 0 state as well. So, this is one example where a binary counter can be used as an exhaustive pattern generator. So, it is not detailed here, but you can check, like if you start with any pattern, say 0 0 0 0 and go on giving clock to this flip flop. So, these are actually flip flops x1, x2, x3, x4, these are flip flops. So, if you go on giving clocks to this flip flops, then in successive cycles, so it will generate new patterns, and it will repeat after generating all the 16 patterns. So, 0 to 15. So, it may not be in that sequence, but it will generate all those patterns, and then only it will come back to 0. So, that way can be done. Other possibility is to have complete LFSR. So, complete LFSR is something, the normal LFSR, standard LFSR. So, this generates this generates the 2 to the power n minus 2 pattern. So, it does not generate the all 0 pattern. Now, here there is a modification. What is done when the cell contents are 0 0 0 1. So, we use a NOR gate here. So, this NOR gate getting all the inputs as 0. So, So, it will make the output as 1 and this 1 and 1. So, that will this XOR gate will output will make 0. So, as a result this cell will get a 0 and in the next cycle this 0 will shift here. So, content of the cell will become all 0. So, that way this circuit this cell will this LFSR will generate all 0 as well, and when the content is all 0 then this gate output is 1 and this also being 0. So, this will become 1 and in that case this 1 will be fed back here and then it will act as normal circuit. So, it will not remain in that all 0 state continually. So, that way this complete LFSR can be constructed from standard LFSR by adding this extra NOR gate. The same is true for modular LFSR, like we can add this extra NOR gate and we can ensure that this is not going to remain in the all 0 state. So, this is some minimization that is done. So, this is basically some logic minimization. By doing this logic minimization, so we can convert this circuit into this, so that this gate count gets reduced. So, here we are requiring 2 XOR gate 1 NOR gate, and in this modified version we require 1 NOR gate, 1 OR gate and 1 XOR gate. Since XOR gates are costly, so this will reduce the circuit overhead. Similarly, here also we have reduced we are requiring 2 XOR gate and 1 NOR gate. In the modified circuit we require 1 XOR gate, 1 OR gate and 1 NOR gate. So, that can be done. We will continue in the next